what I have attempted to draw here is a unit circle. And the fact that I'm calling it a unit circle means it has a radius of 1. So this length from the center, and I centered it at the origin, this length from the center to any point on the circle is of length 1. So what would this coordinate be right over there, right where it intersects along the x-axis? Well, it would be x would be 1, y would be 0. What would this coordinate be up here? Well, we've gone 1 above the origin, but we haven't moved to the left or the right. So our x value is 0, our y value is 1. What about back here? Well, here our x value is -1. We've moved 1 to the left, and we haven't moved up or down. So our y value is 0. And what about down here? Well, we've gone a unit down, or 1 below the origin, but we haven't moved in the xy direction. So our x is 0, and our y is -1. Now, with that out of the way, I'm going to draw an angle. And then the way I'm going to draw this angle, I'm going to define a convention for positive angles. I'm going to say a positive angle, well, the initial side of an angle, we're always going to do along the positive x-axis. So this is you can kind of view it as the starting side of the angle, the initial side of an angle. And then to draw an angle, a positive angle, the terminal side, we're going to move in a counterclockwise direction. So positive angle means we're going counterclockwise. Counterclockwise. And this is just the convention I'm going to use, and it's also the convention that is typically used. And so you can imagine a negative angle would move in a clockwise direction. So let me draw a positive angle. So a positive angle might look something like this. This is the initial side, and then from that I go in a counterclockwise direction until I measure out the angle, and then this is the terminal side. So this is a positive angle theta. And what I want to do is think about this point of intersection between the terminal side of this angle and my unit circle. And let's just say it has the coordinates a, comma, b. The x value where it intersects is a, the y value where it intersects is b. And the whole point of what I'm doing here is I'm going to see how this unit circle might be able to help us extend our traditional definitions of trig functions. And so what I want to do is I want to make this theta part of a right triangle. So to make it part of a right triangle, let me drop an altitude right over here. And let me make it clear that this is a 90-degree angle. So this theta is part of this right triangle. So let's see what we can figure out about the sides of this right triangle. So the first question I have to ask you is, what is the length of the hypotenuse? What is the length of the hypotenuse of this right triangle that I have just constructed? Well, this hypotenuse is just a radius of a unit circle. The unit circle has a radius of 1, so the hypotenuse has length 1. Now, what is the length of this blue side right over here? This blue side, you could view this as the opposite side to the angle. Well, this height is the exact same thing, as the y coordinate of this point of intersection. So this height right over here is going to be equal to b. The y coordinate right over here is b. This height is equal to b. Now, exact same logic. What is the length of this base going to be? The base just of the right triangle. Well, this is going to be the x coordinate of this point of intersection. If you were to drop this down, this is the point x is equal to a, or this whole length between the origin and that is of length a. Now that we have set that up, what is the cosine? And what is the cosine? Let me use the same green. What is the cosine of my angle going to be in terms of a's and b's and any other numbers that might show up? Well, to think about that, we just need our SOHCAHTOA definition. That's the only one we have now. We are actually in the process of extending it. SOHCAHTOA definition of trig functions. And the ka part is what helps us with cosine. It tells us that the cosine of an angle is equal to the length of the adjacent side over the hypotenuse. So what's this going to be? The length of the adjacent side for this angle, the adjacent side has length A, so it's going to be equal to A over, what's the length of the hypotenuse? Well, that's just 1. So the cosine of theta is just equal to A. Let me write this down again. So the cosine of theta is just equal to A. It's equal to the x-coordinate of where this terminal side of the angle intersected the unit circle. Now let's think about the sine of theta. Sine of theta, and I'm going to do it in, well, let me see, I'll do it in orange. So what's the sine of theta going to be? Well, we just have to look at the SO part of our SOHCAHTOA definition. It tells us that sine is opposite over hypotenuse. Well, the opposite side here has length B, and what the hypotenuse has length 1. So our sine of theta is equal to B. So an interesting thing, this coordinate, this point where our terminal side of our angle intersected the unit circle, that point AB, we could also view this as A is the same thing as cosine of theta. A is the same thing as cosine of theta, and B is the same thing. B is the same thing as sine of theta. Well, that's interesting. That was just, we just used our SOHCAHTOA definition. Now, can we in some way use this to extend SOHCAHTOA? Because SOHCAHTOA has a problem. It works out fine if our angle is greater than 0 degrees, if we're dealing with degrees, and if it's less than 90 degrees. We can always make it part of a right triangle. But SOHCAHTOA starts to break down as our angle is either 0 or maybe even becomes negative, or as our angle is 90 degrees or more. You can't have a right triangle with two 90-degree angles in it. It starts to break down. Let me make this clear. So sure, so this is a right triangle, so the angle is pretty large. I can make the angle even larger and still have a right triangle even larger, but I can never get quite to 90 degrees. At 90 degrees, it's not clear that I have a right triangle anymore. It all seems to break down. And especially the case what happens when I go beyond 90 degrees. So let's see if we can use what we set up here. Let's set up a new definition of our trig functions, which is really an extension of SOHCAHTOA, and is consistent with SOHCAHTOA. Instead of defining cosine as, oh, if I have a right triangle and saying, okay, it's the adjacent over the hypotenuse, sine is the opposite over the hypotenuse, tangent is opposite over adjacent, why don't I just say, for any angle, I can draw it in the unit circle using this convention that I just set up, and let's just say that the cosine of our angle is equal to the x-coordinate where we intersect, is equal to the x-coordinate where the terminal side of our angle intersects the unit circle, where angle, I'll write the terminal side of angle intersects the unit circle. And why don't we define sine of theta to be equal to the y-coordinate where the terminal side of the angle intersects the unit circle. So essentially, for any angle, this point is going to define cosine of theta and sine of theta. And so what would be a reasonable definition for tangent of theta? Well, tangent of theta, even with SOHCAHTOA, could be defined as sine of theta over cosine of theta, which in this case is just going to be the y-coordinate where we intersect the unit circle over the x-coordinate. In the next few videos, I'll show some examples where we use a unit circle definition to start evaluating some trig ratios.